Good morning, everyone. Welcome to IPE. I hope that your preparation is going quite well and that you're learning a lot from our other video lectures, whether it is reservoir production, drilling engineering, and formation evaluation lectures. Our numerical series has just begun. Hemant sir have recently uploaded a numerical video which encapsulates many concepts in a single video, and it's if you haven't seen that, it is prudent that you go and check that out. Apart from that, stay dedicated and stay persistent, because those are the key things that are eventually going to help you in landing up a good rank. Today, we are going to discuss a very basic but pretty much important concept, which comes quite handy in different domains of oil and gas industry. You will be applying it in drilling engineering, production engineering, reservoir engineering. So this is quite an important concept. So watch the video till the end, and later on we are going to discuss about the application part as well, like where this concept comes handy. So the concept that I'm talking about is Stokes law. So a lot of you people will be knowing about this particular law. Many of you would have done an experiment in the first or second year where you took a beaker, a large beaker, which was filled with a particular fluid. Be let's say maybe it was water or it could have been mercury, and you took a solid spherical ball and you dropped the ball inside this beaker. So what you would have noticed is that initially the ball, it accelerates as it moves down. It accelerates. Its velocity keeps on increasing, but eventually there comes a point when its velocity becomes constant, and then it moves downwards with that particular constant velocity. So Stokes, what he did, he conducted this experiment and he came up with the numerical derivation of that particular velocity that we achieve. Have you ever wondered why the raindrops that are falling from the sky, since they are falling from such a great height, as they land upon your head or on the buildings, why is that they doesn't kill you or they don't destroy the buildings? Well, that is what is being justified by Stokes' law. As the droplets are falling, obviously they will accelerate at first, but somehow there will be some other force that will balance out that force of gravity and eventually lead that droplet to achieve a certain constant velocity, and then it just drops at your head, no impact. So basically, as the ball is dropping, there are three forces that are acting on the ball. The first one is pretty much simple. It is falling under its own weight, that is force of gravity. Okay. And since it is passing through a fluid, there will be an upthrust or upward force acting on it by the virtue of the fluid through which it is passing. We all know what that force is called. That force is force of buoyancy or buoyant force, and we also say it is as thrust or buoyant force. So it is acting on the ball by the virtue of the difference in the density. Let's say this is my ball. The pressure acting on the downward side and the pressure acting on the upward side, they are different, because the greater the depth, the more will be the pressure. So the difference in this pressure is what's leading to the buoyant force, and it is basically the weight of the displaced fluid, the weight of the fluid that it has displaced. So that is what comes under my buoyant force. As it is falling down, there is one more force that is acting on it, that is my viscous force. Now Now, how is viscous force acting on this ball? Well, as you can see that the ball is falling, the layer which surrounds the ball, it has the same velocity as that of the ball. But let's say this is my ball. The fluid around this ball will have the same velocity as the ball. Okay, this particular layer, it is moving with the same velocity as that of the ball. The subsequent layer of fluid, as you move away from the ball, my velocity is continuously decreasing, and as soon as you reach the wall of the beaker, here my velocity of the fluid that is in contact with the beaker, it is basically zero. So you can see that there is a velocity gradient between this and this point. So this velocity gradient is what's leading to that viscous force. And the higher the velocity gradient there will be, the more will be my viscous force. So as initially my ball is dropping, it is accelerating, it is gaining acceleration, it is dropping, its velocity is continuously increasing, as does my viscous force. Okay, so there are basically three forces acting on the ball. One is my force of gravity, other one is my buoyant force, and the third one is my viscous force. So now we'll see how these things, in which direction these forces are acting. If we talk about gravitational force, obviously it always acts in the downward direction. The buoyant force, it will act in the opposite direction of the gravitational force, that is upthrust, it will act in the upward direction. My viscous force, let's say you roll a ball on a surface. Okay, if the ball is moving in this direction, where will the frictional force act? It acts in the opposite direction of the motion. So does my viscous force. It acts in the opposite direction of my motion. Since the ball is dropping downwards, my viscous force, it will act in the upward direction. So initially my gravitational force is making the ball accelerate. Okay, it will continue accelerating and it will keep on gaining velocity. But as the velocity of the ball is increasing, so is the viscous force that is acting on the ball. Okay, eventually there will come a point when my upward force will become equal to my downward force. When this happens, my overall force acting on the ball will become zero, implying my acceleration becomes zero. My change in velocity becomes zero. At this particular point, my ball will attain the maximum velocity that it can attain while it is passing through the fluid. And that velocity is what we term as terminal velocity. So what Stokes did, he basically derived the value of this terminal velocity by equating the upward and the downward force. So Stokes, he basically conducted various experiments on a spherical ball, and he came up with a relation for viscous force, and what he derived was viscous force is equal to 6 pi eta R V. Eta is my coefficient of viscosity. R is the radius of my spherical ball, whereas V, this one I have to derive. This is the one that I am trying to find, my terminal velocity. And on what parameter does this depends? Okay. Coming to my buoyant force, it is basically the weight of the liquid that has been displaced by my spherical ball. Okay, so buoyant force is basically equal to my liquid density, whatever liquid is there, the density of that particular fluid, Density of fluid I am saying because it can also be gas, like raindrop is falling through the gaseous phase. So in that case, density of fluid. Okay, so density of fluid times the volume of the displaced fluid into G. Basically, this portion is my weight of the displaced fluid. Mass of the displaced fluid is given by density of the fluid into volume of the displaced fluid into acceleration due to gravity. Okay. How much will be my volume of the displaced fluid? If my spherical ball is passing through this liquid, obviously the amount of fluid that it displaced will be equal to the volume of the sphere itself, since it is completely immersed in the liquid. So what will be my volume of the displaced fluid? It will be equal to my volume of the spherical ball, which I can write as 4 by 3 pi r q times g. Okay, and then comes my force due to gravitational force. That's pretty much simple. It is my mass of the sphere into acceleration due to gravity. Mass is density of the spherical ball, okay, density of the ball times the volume of the ball, which is 4 by 3 pi r cube times g. Okay, so note these things down. We'll proceed further. And now everything we have to just balance the upward force with the downward force. One more thing, you might have gone to an amusement park or something. When you are coming down a roller coaster, you would have imagined this thing, what I was telling you now, that as the velocity of my ball is increasing, the frictional force is increasing. So when you are going down the roller coaster, and as your velocity is increasing, the force that the wind is exerting on you, it also automatically increases. So with the same analogy, the same thing is happening over here. As the velocity is increasing, my viscous force is increasing, which eventually balances out my downward force. So force upward is basically buoyant force plus viscous force. This will be equal to my force of gravity. Buoyant force, we have seen density of fluid times 4 by 3 pi r cube times g, plus viscous force, as we discussed earlier, 6 pi eta rv, and this is equal to my gravitational force, which is density of the ball into volume of the sphere into g. Now if I bring this thing to this side, what I will be left with, 6 pi eta rv is equals to, I'll take volume of sphere common because it's common in both these things, and acceleration due to gravity. So it is density of my ball minus density of my fluid. Okay, this get cancelled out, this get cancelled out, pi gets cancelled out, 1 r gets cancelled out. Okay, cube becomes square, and what I'm left with, my value for velocity, it will come out to be 2/9, 3 times 3 9, then r square times g divided by eta, that is my coefficient of viscosity, times density of ball minus density of fluid. So this is the relation that I come for my terminal velocity, Vt. This is the maximum velocity that my ball will acquire while it is passing through a particular fluid. Okay, and as it is falling down. Mind it that this relation 6 pi eta rv, it is applicable only for spherical objects. Okay, this entire derivation is applicable for spherical objects, and my terminal velocity, since it is proportional to r square. Okay, so the greater diameter of my spherical ball is, the more impact it will have on my terminal velocity. My terminal velocity will increase tremendously as the radius of my spherical ball increases. Coming to the application part, in drilling, what you will notice is that when it comes to packer setting, I don't know if many of you will know what a packer is. So what we have is basically, let's say we lower down the tubing into the hole. Okay, we make perforations via the perforation gun. Before making these perforation, that is before connecting my reservoir to my tubing, I have to ensure that my annulus, this space between the tubing and the casing, okay, this empty part is what I call annulus. This part, empty part, is what in oil and gas domain we call as annulus. So I have to isolate my reservoir from my annulus part. So fluids that will come, so that they don't go up the annulus, I have to isolate this. So for that I basically set a packer here. It goes on my tubing, and what I do, the packer, it's a rubber sealing element, so it inflates and it grips onto my casing, and it sort of, like, let's say this is my tubing. Okay, so this is my tubing, it goes downwards. Here I have installed my packer assembly. Okay, so to activate this packer so that it can inflate, what I'll do, I'll drop a ball from the very top. I'll drop a ball from my Christmas tree. The ball, it will pass through, let's say, all the distance. It can be 1,000 meter or 2,000 meter, and it will reach my this area. Here I'll be having a particular nipple assembly or whatever, and my ball, it will reach here and sit in the seat. Then I'll apply pressure from the top. As I'm increasing pressure, this packer will have a certain pressure limit at which it starts inflating. Okay, now since my ball has come here in this portion, it has basically sealed my entire tubing. So as I'm pressurizing from the top, all the pressure is acting on my pressure packer. Okay, and as my packer setting pressure is acquired, let's say it was 1500 psi, this packer will inflate and it will grip onto my casing. Okay, it will inflate and it will grip onto my casing, so that my tubing and casing annulus side, it becomes isolated from my reservoir fluid. So since I dropped the ball from the very top into the tubing which is filled with let's say completion fluid or whatever, here also this principle applies. Stokes law principle applies, and the time it takes to reach here, that can be calculated based upon the constant velocity that it acquires. So this is the concept that where my Stokes law is applicable. And if some of you might be wondering, like, since my ball is set here and once my packer is set, how will my ball go down? So we have the last part of the tubing is what we call as pump out plug, pump out or pump off plug. Okay, so what this particular thing has, it has a seat where this ball will go and rest. Okay, and it has pins. Each pin, it has 10 pins, and each pin has a pressure rating of 500 psi. Now let's say I install 5 pins into this thing. My packer will get set at 1500 psi. Okay, and once my since I have installed 5 pins into this thing, so 5 into 500 is 2500 psi. So once my pressure reaches above this pressure, it will shear the pin and my ball will drop down. Okay, so my ball drops down. Now there is a communication between my reservoir and my this thing. and then my production can take place through the tubing. Okay, so this is just extra knowledge. Uh, when you will go and work in the oil and gas industry, you will come to know about these things. But this is the standard procedure. So the Stokes law was applicable in this case. Another case that you come across is, let's take a separator. So in the surface facility, when your fluid passes through the tubing, it passes through the Christmas tree. In Christmas tree, we have different walls, as other teachers would have discussed. It has been discussed in the production part, and as it passes through Christmas tree, it goes through flow line, then it encounters separator. So what separator is used for is basically it separates your oil, water, and gas. Okay, separator is a unit which is used to separate your crude oil, and it removes water and gas from it. So as it enters the separator, it hits the inlet diverter first. So what happens is, my something mechanism like this happens. Okay, here we have water, since water is the densest, and then comes your oil being lighter than water, and then we have gas on top. Okay, and from here gas gets out, from here water gets out, and then there is a dump valve from which my oil will be taken out. So what I require is that my oil droplets, which are entrained in my gas, as my gas is passing through this, it will have my oil droplets entrained in it. What I want is that I don't want my oil to get lost with the gas, because what we do majority of the times, what we do with the gas is we flare it. So this, like, economically this is not feasible, because I'm losing a lot of oil. These oil droplets will go and get like entrapped in there, and they will leave out. So even in this our separator is designed in such a way that my oil droplets, they should acquire terminal velocity and they should fall under their own weight. Like a drag force is acting on them, and I want my droplets to fall under the effect of gravity into my oil. So in this case also, my Stokes law, it comes handy. Okay, so this was a very important concept that I felt that we should discuss it, as you will be encountering it in many other various concepts. So that will be all for today from my side. Thank you very much.